In the second lecture, we'll start looking at the linearized supersonic flow. And in the supersonic flow, we will first try to calculate CP, which is very important. So using CP, we can calculate the lift and the drag. So using the CP in the supersonic flow, we would also try to define or introduce wave drag, which is also very important and unique in the supersonic flow. Let's start again with a 2D linearized perturbation velocity potential equation. And we've seen this form earlier, and we know in the subsonic flow, 1 minus m infinity squared is positive. But have you considered if it's supersonic flow, 1 minus m infinity squared is a negative value? And this will change the elliptical equation into a hyperbolic equation. So this is what happens from subsonic flow to supersonic flow. It will change the nature of the governing equation, and then the way to solve it should be completely different. Okay, so now what we do is replace 1 minus m infinity square by lambda square. So this is what we the assumption, and we assume the this governing equation has a solution in the form of phi equals fx minus lambda y. And can you demonstrate if it's correct? Okay, so what you can do is just plug in y equals phi fx minus lambda y into the governing equation, and then you will find the left-hand side becomes 0. Okay, so it's I think it's quite straightforward. And now in order to solve it, we assume phi is constant along lines of x minus lambda y equals constant. So phi is constant along a series of parallel lines. And maybe it's hard for you to imagine. So let's see such a figure. And we have a flow surface where a hump is included. And so we are not talking about the hump now, but we can see there are a series of parallel lines. Those are the lines where phi is a constant. Okay. So the slope of those lines, parallel lines, is 1 over lambda. And it becomes 1 over square root m infinity square minus 1. I don't know whether 1 over m square root m infinity minus 1 reminds you something. Does it ring a bell to you? I give you a few seconds to consider, to think. Okay, so do you remember the definition of Mach angle? So in supersonic flow, the Mach wave has an angle of mu, and tan the mu is exactly the same as dy dx. So in this case, our solution of phi is actually along the Mach waves. So is that coincidence? I don't think so. It's just what it is. Okay, so the solution line overlaps with the Mach lines, and our solution will be along the Mach lines. Okay, let's move on. And now we are trying to address the question we proposed at the beginning: how to get the pressure coefficient in the supersonic flow by using of the information of Mach lines. Okay, and and we know u prime is partial phi partial x, and it's f prime. V prime is partial phi partial y is minus lambda f prime. Okay, so by combining these two, we know u prime equals minus v prime divided by lambda. And at the boundary, so along the wall, we know v prime equals u infinity times tan the theta. We get this by applying the small disturbance assumption by eliminating u prime. So it's not listed in here, but you should consider the velocity triangle. Okay, because theta is a small angle, we can further estimate u prime, v prime equals u infinity tan theta. So tan the sign is removed. Okay, so we have u prime and a v prime now. And so we can combine that two. We know u prime equals minus u infinity times theta divided by lambda. And in the earlier lecture, we derived Cp is minus 2 u infinity divided by 2 prime divided by u infinity. Okay, so by plugging u prime, we can find theta equals twice theta. Cp equals twice theta divided by m infinity square minus 1. So this is a pressure coefficient in a supersonic flow at the surface. And you see the derivation is much quicker than in a subsonic flow. Is that right? Okay, so now let's see how can we make use of this. Before we start using it, we need to define when the theta is positive, when theta is negative. So that's very important. And you can see Cp is directly proportional to the local surface inclination with respect to the free stream. It holds for any 2D slender body where angle theta is small. Okay, so if the deflection is the surface deflection goes into the flow, then it's positive deflection or positive theta. If the surface deflects deviates from the flow, it's a negative deflection, so theta is negative. So considering this hump or little bump, the forward portion, so if it's symmetrical, the forward portion deflects the flow in deflects the surface into the flow. So theta, we have positive theta. And if we look at the rear portion or backward portion, the surface deviates from the flow, so theta is negative. You can see clearly the sign of the deflection angles. So on the forward surface, the Cp is positive, and on the rear surface, the Cp is negative because of the sign of theta. Okay. Then we know the pressure over the forward surface is larger than the free stream, and the pressure on the rear surface is smaller than the pressure in the free stream. Okay, knowing that, we have a downward force, pressing force onto the hump, but there's a suction force at the rear, so we can see the difference by doing the projection. So if we look at the horizontal force, so we can do the projection of the total vector, total force vector, and we can see there are the two horizontal forces are pointing towards downstream. So these two forces, two little forces, combines into drag. So there is drag. This is how we get drag in the supersonic flow, although we assume the flow is inviscid. So there is a drag. So this drag is associated with the Mach waves, and we call it the wave drag. So this is very unique in the supersonic flow. This is how we get the wave drag in supersonic flow. So this is a very important concept. And now we can close this mini lecture. So in this mini lecture, we derive the Cp distribution on the surface and also the introduction of the wave drag. Why it's called wave drag and how it is produced.